Thank you for coming. Actually, wait, could you close the door maybe? That's probably a good idea. I don't know if people are. Well, I guess no one's taking the final here.
Yeah.
Anyway.
It's like this hall's all faculty office.
Yes. Well, I don't want to annoy Baseline. I think he's right there. So. Okay. Well, everyone, thank you for coming for my presentation. No, it's fine. Sorry. So, my project is called C Parsec. That's how I pronounce this, even though there's a second P in the middle. It is a C++ implementation of the Haskell library Parsec, which we'll talk about in just a moment. So the main objectives is to port that library over to C++. And as you're going to see, this is a tremendously difficult task for a lot of reasons. And secondly, because C++ is still a very quickly evolving language, I also wanted to see how the newer features they added play along with trying to do something which is very out of the scope for normal low-level system languages. So, out of these two goals, I actually think I did both of them, and you're going to see that in action. And now let's talk about what is Parsec. And here I have the logo that the library comes from for the language Haskell. So it's a parser combinator library. So a parser combinator library is kind of like parsing with Legos. And parsing is when you turn text into a concrete type. So if you want to parse a number that's inside of a quote, you got to turn it into a real number. That's what parsing would do for you. So parser combinators have two main parts to them. You have atoms and you have the actual combinators. Atoms are very simple parsers. Like a parser for a single character, all it's going to do is take your text, parse a single character, and then return that character with the consumed part of the text you get. A string will do the same thing, but for a whole string. And then you can, from those two very small things, you can build the rest of your parsers that you need. So for example, you might also want to figure out digit and uppercase, but those are all just derivatives of character. If you can parse a single character, a single atom, you can build anything. So for the combinator stage, we'll have to give a few examples here because they vary very drastically. So one of these is called many. So many will take a single parser that we'll call P here. And what it does is it parses as many P's as it can find, and then it stops, and it's going to return them to you in some sort of collection, probably a list. Another one that's important is OR. If you have OR, it takes two parsers that we call A and B here. So if A, what you do first is you go left to right, just like the OR operator for Boolean logic. So you parse A first, and if A fails to parse, only then do you parse B. And generally A and B are going to be the same type, because it would be strange to parse a number or a string, because if you want the same return type, that makes it a lot simpler to use. One other simple one is called count. It takes two parameters, a number n and another parser p. And all it's going to do is parse p n amount of times. So you can see that we're going to be able to use these to combine our atoms to create fairly complicated parsers. So I'm going to give a few examples here inside of Haskell, but simple examples that you should be able to just eyeball your way through. So let's say that a number string is the parser we want to create, and all it is a bunch of digits. So here's the type here. We have number string, and it's a parser that's going to parse a string. So the definition is actually quite simple. It's a single line. A number string is a bunch of digits, at least one. That's what the one inside of many one is. English doesn't really have an easy way to say 0 or more. So many by default is 0 or more of whatever you want to parse, and many one is 1 or more. So we would use many one here because a number string probably has to have at least one character for it to be a number, right? There's no number that's just blank. So that's why that's using many one. So another one is name, right? So let's define a name as something that's uppercase, an uppercase letter, and it's followed by a bunch of other letters. Uppercase or lowercase, doesn't matter. So same thing here, it's still going to parse a string and give you a string at the end of it when it's done. And this is a little bit more complicated. Just see the arrow as an equal sign. So what we have here is that we're going to get an uppercase letter, that's upper, and we're going to save it in a variable called first letter. And then we get the rest of the name. That's the name for that second variable, and all it is a bunch of letters, 0 or more. So what this actually does is it allows you to have a name that's just a single uppercase letter. Don't know why that would happen, but it's possible. And now that we have the first letter of the name and the rest of it, you can combine them together and return them. It's a little bit weird here. Basically, you've got to turn the first character into a string, and then you combine it with the rest of the name. So that's what that's doing. You might be wondering now, error handling, right? So when you're parsing something, you might get mangled input or something that's not correctly formatted. So what actually happens when this fails? So let's look at the case where it doesn't fail first. And how you would use this roughly kind of looks like this. So you would have some sort of parse function, and it's going to take your parser and then some sort of string input. So in this case, we just want to print out the result of what we get. So if we parse John, we'll actually get John at the end. And what happens is that the first letter J is turned into a single character J. The rest of it is OHN, that's the rest of the name, and then we combine them together for John. So if we give it a lowercase letter first, what happens? Well, we get an error. So what you'll notice is that there's no explicit error handling inside of this library, right? We don't actually do any manual error checking, which is very good. Because having to do this for everything is very annoying, right? If at every single time you wanted to do a parse and you had to manually validate it, things would get messy and very large and just difficult to read. So we don't want to do that. It's all done by default. And that's something else that we implement for this library. So I'm going to show you how this looks in my library now. So like we said, number string is just a bunch of digits, and that's the implementation you just saw. And this is what it looks like in my library. So this is pretty much the exact same thing. So you can see that I have a parser type that contains a string called number string, and all it does is it returns the exact same thing, at least one digit. And you can also write it as a variable. That would be I think you can see here visually these are identical. So this works. The library basically does what it needs. So we can show the same thing with name. Now name looks a little bit different because unlike number string, we actually give a name to pieces that we're parsing. First letter and rest of name. So in this current way, it's not obvious how you give a name to something like that, right? Because if your variable evaluates to something, there's no place to give it a name in between. So what I end up doing is that I have a macro here, and there's a lot of macros here, which we'll explain a little bit in detail later. So just ignore that, it's just making the parser that we have. And then I have one key macro here called save. What save does is it assigns the result of a parse to a variable name, exactly in the same way as Parsec does. Ordinarily, there are a lot of challenges to doing modifications to variable names like that, so that's why I have to use a macro here, two ways that you'll see. And you can see that at the end, we just return the character string, the string of the first letter turned into a character with the rest of the name. So that's identical to, again, how Parsec behaves. And yeah, the key difference here, right, is that we're allowed to have name bindings for both of these, which I don't think there's any other Parsec or Parsec community library right now that allows you to do that. And there are probably good reasons for that, but we made it work. So the actual requirement is that we do everything Parsec does, and we have the dot syntax for methods, because in the original library, there's no dot syntax for methods. That's just the quirk of the language. It's very complicated. But they're good in general. Most languages have some sort of dot syntax by now. It's good for composability and such. So, and I had a couple of bonus goals as well. So I wanted to be able to make it so that you could parse anything, not just strings, but anything you wanted, JSON, byte strings, other such. And I also wanted to benchmark it against other libraries, which did not end up happening. So the first two I actually did end up doing. But yeah, I only had time to test my own library, and the only other library that I could find was Boost. And I didn't find out that it existed until a month into the project because they didn't actually prove it. It's still not inside of Boost. It was just in the preliminary stages of being accepted right now. So that's still not in the library, so I didn't even test it. Let's think about the implementation a little bit here. So what is it that allows you to return one thing, which is either the parse you want to type or an error, right? When we tried to parse the lowercase John, you saw that we got an error, right? So what we'll have here is a template, generic type, that will take any type parameter t. And the parse result, whenever you parse anything, it's either what you want to parse or it's a parse error. And the parse error is a class that does a bunch of other things to make error handling easier. But essentially, that's the main of it. When you call parse on a parser, it's going to give you either your thing or an error. So yeah, that's what this expected type is. It's also very new. It's in C++ 23, I believe. So that's one of the newest features I've been using that works pretty well. It has a lot of downsides, but it's helpful just so that we can get this behavior of one type essentially being two things. The parser class is a little bit complicated. We'll just kind of skim over it. So the only thing that parser class actually holds is a single parse function here, which is just a function wrapper for something that will take your input type, in this case a string, and return whatever your output type is, the parse result t here. So in terms of the actual methods we have the parse function we need here, which, like I said, will take your input type and return a parse result. So the actual parse class is very small. It only actually holds one little piece there. That's the only concrete thing it actually owns. The rest of it is just functions. Hey, Lam, what's up? Okay. And yeah, so that's inside of the core file here. So like I said, all it does is that it takes your input, and all it does is parse it, and it returns the result of parse it. So it's actually, that's the entire definition of parse. It's actually not very complicated. It just takes your input and gives it to your parser. Yeah, and that's the actual parser here, remember, it's just a function that takes your thing and returns the type it gets. So in terms of methods, there's a bunch of them. I mean, it doesn't really matter exactly what they are concretely. Like I said before, we have try, right? Try the parser on the left and then the parser on the right. That's probably the most important one. But yeah, they do a lot of different things. You can combine them in very different ways. You can have it skip the second parser if you have two of them, or skip the first one and only do the second one. Things that are very handy overall. And then there's all the other parsers I implemented. Right, we see OR again there. Count we talked about before. There's more of them. There's more of them, and there's more of them. And then, okay, this is actually important, the operators. The other interesting thing that C++ lets you do is that it allows you to overload operators. Some languages have banned this on the case that it gets abused. That's like kind of true, I guess, but it does allow you to have some pretty nice syntax for a lot of things, especially for using OR, right? There's nothing wrong with calling .or on a parser. I see no issue with that, but it's semantically, I think OR is perfect for this task, and it even does short-circuiting. So I think, or mostly short-circuiting for this. So I don't see an issue with doing operator overloading for this, just because it's very handy. And we get some very long types down here. This is for AND, right? If you want to parse two things and keep the result of both of them, you could use AND, and that's also very handy. So then we have some extra things for reporting errors. So we'll look at just one implementation here and look at three different ways to do it. It's called between. So between, you can see, takes three parsers: open, close, and p. So the first implementation uses the operators that are overloaded. You can see that what this is going to do is it's going to parse open and then give through whatever's on the right-hand side, which in this case is p. And then it does this one, which is left shift, overloaded, such that it gives you whatever's on the left-hand side. So this one gives you the thing on the right, this thing gives you the thing on the left. So the result is that if you want to parse something between two other parsers, you can use this, because it's going to give you the middle. This will also be written with explicit operators. You can say with, give you the thing on the right, and then skip, give you the thing on the left. It still performs each parse, it's just selectively ignoring which parts you don't want to do. And this is more in the Parsec style, is what I would call this. So you can see this time we actually give a name to the middle. So open parses here, and it skips the result because it doesn't need it. Then it parses p and saves it to something called middle, then close, and then it actually returns middle. So I think that's a little bit handier just because it gives you names, right? So operators, methods, and then the Parsec style that allows you to do name bindings to your parses. And inside of Parsec, that would be the implementation. You can see that it's very similar, just without the macros. Okay. In terms of core parsers, right, we have the main parsers I talked about before, right, character and string. Those are the only important ones that you need. The rest of these are just derived off of other characters. And I specialize these to strings such that it's easier to use them, to combine them, because when you have a vector of characters, that's different from having a string. So we'll look at the implementation for a character now, which is a little bit intimidating because there's a lot of macros in here as well, but it's not actually that complicated. So if you have a string and you're looking for a single character C, if your string is empty, then you can't do anything. That means you failed. If your string, the first letter inside of your string is not C, that means it's also, you failed to parse, so that's also an error. But if they match, if this is not the case, that means you can get rid of the first character and now return it, because you found it, consuming the first character. Any character is even simpler. If your input is not empty, that means your parser has worked, so you can just return the first letter inside of it. So that was the core of the parser and the character specialization inside of it. So the actual header that you include if you want to use the base library that I wrote is CParsec.h, and all it does is include the core that I wrote by itself, that's standalone, and character, which fills out a bunch of functions such that you can parse strings, because that's most of what you would want to do anyway. But I did allow this extra feature so that you can actually parse whatever you want. I said I was able to do that, and I actually did. So the second template input to the parser, other than what you want to parse, is by default a string. But if you want to parse something else, you can do that. You can plug it into the second type as long as it follows a few rules. And I actually did that. So I wrote a custom string view that it's not shown here, but it counts how many characters you consume. And eventually that's going to become the base parser, because it's very helpful to find out how many characters you consume for error reporting, because otherwise you don't know where in your input you are. So we'll talk about some of the macros now. So the two main macros that we have are save and make. So obviously this is a little bit complicated, but let's look at save now. So macros in C have a lot of quirks to them. So the base thing with the macro is that it's what they call, I think, token pasting. So it takes whatever you give it, and it'll just replace it into whatever macro you define instantly with no thought to whether it works or not. It's very much on you to make sure it works. The second part that's interesting is variadic macros. So variadic macros can take any amount of arguments, and to access them, you have to use this other macro called VARGs. I assume that stands for variadic. So save here, you can see takes two arguments. It takes a var and then a bunch of other things. Var is the name of a variable. You can see that we actually assign a variable called var here, whatever you replace it with. It could be, I remember most of the time we called it middle for between, right? That's where you would go there. And you can see that all it does is it takes whatever you gave it, which is going to be a parser. It calls parse on the input and takes that. And so remember that when you call parse on something like this, it gives you the parse result. And the parse result either has a value or it has an error. If it has a value, if it doesn't have a value, that's what the if statement is checking, it returns the error it found. If it does have a value, then whatever name you wanted to give it to the variable will have that value. So that's how we're able to actually use the value inside of it without having to constantly wrap and unwrap manually. It's still doing all of that work, it's just like you don't have to see any of it. So inside of between, that's what these macros are doing. So we have skip, which is that, except it doesn't save the result. So we have open, middle, and close, right? And if you expand that out, you get this, which is essentially what you would have to write otherwise, and nobody actually wants to write that, right? Like you would have, every single time you want to parse anything, you would have to say, did it succeed? If yes, continue. If not, then stop, right? And that's a very annoying type of design pattern to have. So the macro does it for you very concretely. There's really no way that can go wrong. And you can see that the top macro, right, is CParsec make. So what exactly is that? Well, it looks like it's taking a parser type, right? The type of thing that you want to parse. In this case, T and whatever input type it is. And that expands to this, which is kind of too long. I don't think it actually fits on the screen. So it didn't, if I could have made it without this macro, I would have. But I could not find a way to make the type checker work with this. Essentially, the problem is that your parser expects, the constructor for your parser expects a function that takes an input stream and returns a parse result. But to get this to work, that means you have to type the parser name twice, in this case actually 3 times because I have a factory. And having to type one type 3 times just to make it once is like a little absurd, so that's what that macro is doing. I'll give you a more complicated example of things you can parse with this. So this is expert, right? So an expression, basic expressions. So the add op here is basically just a function that'll add things, and molop is a function that will just multiply things inside of a parser. These are all wrapped inside of parsers. Spaced is anything that's between a space. So that's, you can see an inline definition to make a parser here. You can see that it takes a p, it's going to be some type of parser, and it's going to take p between spaces and maybe other spaces. And you can see that inside of here we have the 3 things that you can use to compose an expression, also written locally without exterior functions. And these are mutually recursive, which we'll talk about in a second. So a factor is either a number or another expression between parentheses. A term is either a factor or a multiplication symbol, and it's going to give you the multiplication function here. And expert is either a term or plus, and then the add op. So you can see that all of these are wrapped inside, or the bottom 2 are wrapped inside chain L1. That's left associative chaining, right? How you group the parentheses in binary operations. And what this does is it allows you to do fairly complicated types of things with very little code. Like if you wanted to handwrite something that could solve equations like this with, you know, proper spacing and all, and still get you the correct results, that would take a lot more than like 10 lines of code in any other system. So those are the tests, also the test style I used. I used the Boost testing library. And this is also one case where I think my library did a better job than another one I found. That was called Combine. It's written for Rust. There's a little thing called lazy here. I'm not going to explain it too closely, but basically, since a factor is either a number or an expression essentially, if you actually called expression here, because these are mutually recursive, that would expand infinitely. So your compilation would, I don't think, ever finish, or you would Stack Overflow. I think you would actually Stack Overflow in that case. And when I was writing the same thing in Rust, to deal with that, you have to do like a bunch of weird stuff here, right? That's a little bit hard to explain. While in mine, I actually was able to create a parser which will not infinitely expand, essentially. That's what lazy does. Okay, so let's talk about performance to wrap up. So the performance is like, oh, it's okay. It's acceptable, I think. I don't know exactly what the benchmark is, because again, I wasn't able to go with other libraries, but I can do 1 million characters in a third of a second and 2 million characters inside of a string in about 2 seconds. So I think that's an acceptable speed. It does not seem crazy to me. You can see the operations per second here is, even in the slowest case, I think 500,000. And that varies sometimes by the benchmark that we use. So that's release. So yeah, before I talk about the debug version, release is essentially the version of your program that you would actually distribute out to people who want to use it. So if this was included in another library, release is what they would use. The problem with release is that it takes longer to compile. The optimizers that the compiler does takes a lot more work to function. So most of the time when you're developing something, it's inside of debug. So how much slower is debug than release? It's like 100 times slower sometimes. So yeah, the character one in this case was about 76 times slower. The CSV parser I wrote was about 43 times slower. So in terms of performance, I think on the release build, it's actually all right, just going by instinct, but on the debug, it's not great. I expected a 5 to 10 times speed up going from debug to release, but not 40 to 100. So I did try to look at what this is doing. So I'm not good at assembly, and I just very briefly peeked. But in the release version, it looks like a lot of the function calls are, I believe they're called inlining, which makes things go a lot faster essentially. And a lot of the calls I did, a lot of the function calls I do entirely are just taken away. They're not, I couldn't find them in the assembly at all. So the optimizers can be very powerful. You can see literally it goes 76 times faster, right? Once we go from debug to release. But it also means that our debug build is quite slow, maybe unacceptably slow. So let's talk about one major feature here that I use called concepts. So this entire thing is a generic library, right? It uses a lot of templates. But the biggest problem with templates is that the error messages are bad. This is a real error that I got a couple of years ago. Someone actually knew what the problem was, but yeah, like it literally fills the entire screen, and the text isn't even very big. So, you know, that's a sign of how bad things can get. So concepts can constrain templates, and by constraining templates, you're telling the compiler what you're trying to do. And so this allows you to improve your error messages, which makes debugging much easier whenever your templates go wrong. And just to show an example, here's a concept that I named pushback. And all it does is it takes some sort of thing called C for container, and it takes any type T. And if on that container you call pushback on that type T, on something of that type T, it should return nothing, and as long as it can do that, then it's good. It can also do a move, that's also good. If you can't do this, if you pass in a container that can't do this, it's going to say that your type failed the constraints of pushback, instead of giving you gigantic error messages about how it's missing this function and then 500,000 other pages of useless garbage. So where did I actually use this? I used it in many. So the thing with many is that by default, I had it return a standard vector, right? Which is fine, there's nothing wrong with that. But in some contexts, people can't use that. And in that context, that would mean they would have to convert from standard vector to their vector container. So that turns every operation instantly probably twice as expensive, just because they would have two containers being allocated. And in many cases, they can't use it at all. So this would actually just not work for them. So if you want to customize your container, you can actually just pass it in as a argument to that template. So you can not only place anything, you can place into anything so long as your container has the function pushback. So that's what the concept does. And we'll talk about the actual bug I got, probably the worst bug I've ever gotten. So this is called ICE, Incomplete Compiler Error, ICE. And when this happens, it doesn't mean you wrote your code wrong. It means there's actually a bug with the compiler. And there's usually never a bug with the compiler. People think it's the compiler. It's not. This actually was a problem with the compiler. Like, I filed a report and they're looking at it. So yeah, definitely one of the more interesting moments, because I also don't understand what was causing it, even though I fixed it. So yeah. Okay, so since we're wrapping up, let's go with some takeaways. So Parsec combinators can actually be implemented and used safely in C++. It's very difficult to get there, but it's actually possible. C++ is by far the most complicated language that I know. It's also very powerful. A lot of the problems, every single week I would run into a problem that I thought was impossible. I was like, syntactically, semantically, there's no way to express this. And then I found a solution. This happened about 3 months in a row. So yeah. And even after that, I still feel like I know less than half the language, which I think kind of is a problem, but that's all right. And yeah, this also could have been 5 hours long. Like, the amount of stuff I cut out is painful to me, because I spent so much time on it and I haven't even mentioned a single word about it, but that's okay. Thank you for coming. Any questions? That's about what I expected. Sorry. Okay, good. That was about 24 minutes. That's about what I planned. Yes. Okay.
What would be like a potential implementation of this library?
Use or
use case, sorry.
Okay, honestly, the thing is, Parsec combinators are like kind of nice, but they're not used terribly widely. They're not used, but they're also not that common. So in the case where you want to define something kind of complicated, but performance is not critical, that's a very good time to use a parser combinator.
Okay.
Like if you want to write your own language and you want to parse it, which is a surprisingly difficult step in some cases, it's really, really, really easy to parse something using Parsec for this. Like you saw that we could do the expression one, right? Something that's relatively quite complicated inside of, I think, just a few lines. So that, right? Like if you want to be able to parse any arbitrary combinations of potentially nested parentheses, spaced out arguments, multiple different types, right? That would take probably a while to do it by hand, and certainly a while to do it correctly, right? But inside of this is done. It's like 1, 2, 3, 4, 5, 6, 7, 6 if you don't count the declarations. So 6 lines to do that.
Got it.
That's one very famous case is pretty much recursive structures especially, I think. So languages mostly. And
In your
What gave you the motivation to do this for a project?
okay, so I found out about this library in my Haskell class that Paul Downer teaches. It's very good. And I was like, this would be helpful for so many things. Like, I actually want to use this. And I started looking around, and they exist in other languages. Python has one that's okay. It's not great, but it's okay. Rust has a decent one. It's very complicated because Rust is complicated. And C++ has a bunch of parser combinators, but they don't look like Parsec. Most of them are for what they call DSLs, like domain-specific languages. So they don't really look anything like this does. Like you can actually map my language, my library to Parsec 1-to-1. You can't map any of the other ones to that. So Boost comes close. Boost sort of does everything like this style. It doesn't do the name binding that I did, and I think I show it in the macros, right? It doesn't have the name binding. No library I found has this name binding ability where you can give a name to something you parse. Or if you don't want to, then you don't have to, right? Like I think I showed the other ways to implement between, right? There are 3 different ways to do it. You can do it, you don't have to name anything, or you can name it if you want. I think it's very handy to do that. So that's essentially that. Did you say something?
in the benchmarking tables that you had,
Yeah.
you know, there were like time hops per second, but there was also an error percentage. What
Oh.
does that column mean?
I think it's like, okay, so it basically means I have to run a lot more tests. So they said 5% was really bad. So I ran, I think, 1 million characters to test this with the parser, and they said to get the stable error rate, I think it's reproducibility of your benchmark time. I would have had to do like 10 million or something. It's fine. I mean, that's only 3 seconds, I guess, but this would have been 4 minutes long if I did that. So I didn't feel like waiting that long. So yeah, you can see that because each operation is so cheap, this is called micro benchmarking. I think the library is nano benchmark. So micro benchmarking is really difficult because I think a bunch of tiny factors in EPC can influence the time by a lot. So basically, did you say what the error was? I forget.
Yeah.
Oh yeah, so yeah, that just means like I need to do a lot more cases. And each of these are at least 100,000 cases each, and even that's not enough. So some of these really want like 1 million. Or in the case of a character, which is super cheap, like literally 10 million to get a stable rate. So yeah, it was difficult to find that. And again, I didn't have a chance to benchmark the other libraries because I didn't actually get a chance to use them. So yeah.
Did you benchmark the Haskell one at all?
Okay, that one I could have done in 5 minutes. I just forgot completely. So my original goal was to benchmark mine, other libraries, then Parsec, and then the one in Rust. And I didn't end up doing any of that, I'll be honest. But I honestly guarantee, like for the base case, mine is faster. Because I feel like how much faster than like 40 million operations a second can you get, like reasonably, right? Everything else, there's probably a lot of overhead. Like a CSV parser is not that complicated, but you can see that it's already like 100 times slower. So honestly, I think there's a lot of overhead using my library. It's not like, I don't think it's fatally bad. I would have to try a really complicated parser with a bunch of pieces attached to see if it's fatally bad, but I did also text expert, which has a lot of things, and I think the growth rate in time is like, I don't know, logarithmic or something. I don't think it gets exponentially worse, at least. I'm pretty sure about that. So, yeah. Okay. So I think we're good. All right. Thanks for coming, everybody. Oh, that was a lot.